Hi friends, how are you all guys? I think you all are fine in home. So please stay at home. Today I am going to discuss about the time independent and non-degenerate perturbation theory. So last class we discussed the introduction to perturbation theory. Today basically we will discuss what are the corrections like first order correction to energy eigenvalue and eigenfunction. So let us start the topic. So let us start. Time independent and non-degenerate perturbation theory. And what is our aim? Our aim is find out the energy eigenvalue. So energy eigenvalue En and eigenfunction psi n. This is our aim, to find out these two values, these two correction in perturbation theory. Okay, so how we can establish the relation and how we can find out the energy eigenvalue and eigenfunction. So first write down the Schrodinger equation. Okay, H psi n H cap, this is the operator, Hamiltonian operator. That means it is total Hamiltonian operating with energy eigenvalue psi n, giving the energy eigenvalue En, multiplying with same eigenfunction psi n. So this is our required Schrodinger equation. Okay, this is equation number 1. We already discussed about the total Hamiltonian in the last class, so please go back to the last class of my perturbation theory. So H cap, this is the total Hamiltonian, H naught plus lambda H prime, this is unperturbed Hamiltonian, this is perturbed Hamiltonian. Okay, so this is equation number 2. Okay, so instead of H cap we can write out the second equation. Okay, so please put the second equation in the equation number 1. So H naught cap plus lambda H prime operating eigenfunction psi n, giving the energy eigenvalue En, multiplying with same function psi n. Okay, so this is equation number 3. Okay, so we can write eigenstate psi n In0 plus lambda psi n1 plus lambda square psi n2, like that. We can write eigenfunction as a power series of lambda. Okay, it is convenient to write the power series, and we can write similarly, we can write En also, En0 plus lambda En1 lambda square En2 plus. Okay, so we can write in terms of power series both eigenfunction and eigenvalue. Okay, so these superscripts 0, 1, 2, okay, these are the order, like 0 is the 0th order, 1 is the first order, 2 is the second order. Okay, so let us put these two psi n and En in equation number 3. So put H naught cap plus lambda H prime psi n, power series of psi n is psi n0 plus lambda psi n1 plus lambda square psi n, giving this En. We can write the power series instead of En. Okay, so En0 plus lambda En1 plus lambda square En2. Okay, with the same function psi n0 plus lambda psi n1 plus lambda square psi n2. Okay, So we can equate the coefficients of equal powers of lambda in both of the sides of this equation. So this is the equation. Okay, we can equate the coefficients of lambda. This is the coefficient of lambda, this is 1. So coefficients of lambda in both of the side of the equation. Okay, so let us do it. So term free from lambda. Okay, first equate term free from lambda, that means lambda raised to 0. Okay, term free from lambda, we can get h naught cap psi n0 is equal to en0 psi n0. Okay, so this is equation number 4. So term free from lambda, this is the equation, Schrodinger equation of h naught cap. Then term coefficients, or we can write coefficients of lambda square, lambda, coefficients of lambda. So when we can equate the coefficient of lambda from both sides of the equation, we can get what we can get actually h naught cap psi n1, okay, plus h prime psi n0. I wrote from this equation. Okay, this is the given equation. We can equate the both of the side of the lambda and lambda square, coefficient of lambda and lambda square from this equation. So we can get that this term is equal to en0 psi n1 plus en1 psi n0. Okay, so this is our required equation. So now the work is, we can write psi n1 in terms of psi m0. How we can write? am1 psi m0 sigma m. We can write psi n1, this one psi n1 in terms of psi m0. Okay, so now where am1 is the expansion coefficient to be determined. We have to determine this coefficient. Okay, so give the equation number 6. So put equation number 6 in the given equation number 5. So h naught in place of psi n1, you can put this one. Okay, so sigma am1 psi m0 plus h prime psi n0 is equal to en0, again sigma am1 psi m0 plus en1 psi n0. Okay, so in this equation, when this h naught cap, this is the operator on perturbed Hamiltonian operator. Okay, when this one goes to inside, it will becomes em0, the eigenvalue em0. So in the next step, this one is the line am1 em0 psi m0 and all are same. Okay, so the next work is what we can do in the next step. So we can integrate. Now the times for integration. Okay, so we can multiply psi k0. This is the complex conjugate of the ground state wave function. Okay, and we can multiply this wave function psi k0. This is the complex conjugate. Okay, and integrate the space tau. Okay, we can integrate this over the space tau. Okay, so let us do it in the next step. So the next step is sigma m1 em0 psi k0 star psi m0 d tau integration plus integration psi k0 star h prime psi n0, okay, d tau. Okay, then in the right hand side also we can multiply this wave function and integrate over the space tau. So en tau is the whole space, okay. So en0 sigma am1 psi k0 star psi m0 d tau integration plus en1 psi k0 star psi n0 d tau integration. Okay, so what is the next step? We can write k by m, okay, as del km, okay, or otherwise we can write integration of psi k0 star psi m0 d tau as del km. Okay, so put this term into the given above equation. So please do it. So next step is am1 em0 del km plus h prime kn is equal to en0. Okay, en0 sigma am1 del km, okay, plus en1 del kn. Okay, so the next step is ak1 em0 h prime, this one is h prime, okay, this one is h prime kn is equal to en0 ak1 plus, okay, so this one is en1 del kn. Okay, so what we can write in the next step? So en1 don't worry del kn. So in the next step, this term we can take this term into the right side and we can write. Okay, so please do it. So this one is ak1 en0 minus ek0 plus en1 del kn is equal to h prime kn. So this is our required equation. So give the equation number a here. Okay, so let us write case 1 and case 2. So first case 1 is k is not equal to n. Okay, when k is not equal to n, so this one becomes what? 0. When k not equal to n, del kn becomes 0, right? Del kn becomes 0. Okay, so delta kn equal to 0, that means we can write ak1 is equal to what? H prime n or k not equal to n, that means kn divided by en0 minus ak0, where k not equal to n. Okay, so this one, the expansion coefficient which we already determined. Okay, so this one is 0 when k not equal to n, this one is 0, these terms will going to means 0. Then what is the value of expansion coefficient ak1? ak1 is equal to h prime kn divided by en0 minus ek0. Okay, so this is our equation number 7. Okay, so here is the equation number 7. So ak1 we know it is the expansion coefficient which is already determined. Okay, so the question is, what about the first order correction to wave function or eigenstate? Okay, so psi n1 we know psi n1 is equal to sigma m am1 psi m0. This one the value of psi n1. So this is the ak1. We can write instead of m k. So we can put this value in this equation. So it will become psi n1 is equal to sigma k not equal to n h prime kn divided by n0 minus ek0 into psi k0. So it is equation number 8. So this is the equation number 8, is known as first order correction to the eigenstate psi n1. So now we can go for case 2. So in case 2, k is equal to n. Okay, so case 2, k is equal to n. If k is equal to n, so this term becomes 0. This term becomes del kn is equal to 1. So en1 is equal to h prime nn. Okay, so the en1 is equal to h prime nn. So what is the first order correction to energy eigenvalue? This one h prime nn, equation number 9. So we can write en1 is equal to en0 plus h prime nn, equation number 10. And we can write psi n1 is equal to psi n0 plus sigma k not equal to n h prime kn divided by n0 minus ek0 into psi k0. So this is all about first order correction to eigenstate psi n1 and eigenvalue en1. So in the next episode we can go for the second order correction. So thank you friends.